One of my favorite evolutionary adaptations to life on Earth is the way that some migratory animals can use our planet's magnetic poles to navigate over vast distances. Even cows and wild deer tend to align their bodies in the north-south direction when they're at rest. Birds, whales, turtles, and other migratory animals can use the magnetic properties of the Earth for navigation. How might this work? Well, it turns out that they have a magnetic sense. Some animals actually have magnetite, or tiny iron-rich crystals, inside the cells of their nervous systems that align themselves with the magnetic field of the Earth, much like a needle in a compass. In some bird species, there is also a connection between the eye and a part of the brain that is involved in orienting the bird during migration, implying that these birds might be able to see the magnetic field of the Earth, much like we see colors or depth. Even though we make use of magnets every day in everything from our refrigerator doors to our credit cards, they still seem a bit mysterious, because we can't see the force that attracts or repels them. Magnets seem to have magical properties. What child isn't fascinated by their properties the first time that he or she discovers them? Like electric charges, opposite magnetic poles attract each other, and like poles repel each other. But one important difference between magnetic poles and electric charges is that electric charges can be isolated from each other. You can separate an electron from an atom and have a negatively charged particle on its own. But if you cut a magnet in half, you just get two smaller magnets with north and south poles of their own. It's like a worm that just regrows a new head if you decapitate it. They can do that, by the way. It's weird. And let's face it, magnetism is weird too. Let's take a look at what we know, bearing in mind that we still don't know everything about how it works and how it affects us. What makes a magnet magnetic? And why call the poles of a magnet north and south? The answer lies in the core of the Earth, where the slow movement of iron alloys generates a magnetic field. If you let a magnet orient itself, one side will point to the geographic North Pole and the other will point to the South Pole. The magnetic north and south poles move around a bit on the Earth because the interior of the Earth changes with time. They're not exactly at the geographic north and south pole or the top and bottom of the Earth, depending on your perspective. And every few 100,000 years, the poles actually reverse, so south is north and vice versa. But despite these slight variations in exact position, compasses have been used to help us navigate the world for centuries. And navigation isn't the most important function of this magnetic field. It also protects us from the harmful ultraviolet rays of the sun. The field deflects most of the charged particles with which the sun bombards us. And if these particles were not deflected, they would erode the Earth's ozone layer, exposing us to more ultraviolet radiation. But how does magnetism work? We first need to distinguish a magnetic field, that is, the area surrounding a magnet's poles that has magnetic properties, from a magnetic force, which is the force that a magnetic field exerts on a moving charge. We talk about fields in terms of moving charges because magnetism is related closely to electricity, which, simply put, is moving electrical charges, or even more simply, moving electrons. Second, we need to understand what causes the field to be created. Magnetic fields are caused by the spin of electrons. We know that electrons orbit the nucleus of atoms following specific orbital paths, but they also have their own intrinsic spin. They rotate the way a curveball rotates on its way to home plate. This spin is intrinsic in the same way that mass or charge is a property of the electron. If an electron is not spinning, it is no longer an electron. As it spins, each electron generates a magnetic field. Since there are electrons in every atom, why isn't everything magnetic? In fact, All materials are affected by the magnetic fields generated by their spinning electrons, but most of them contain elements with an equal number of electrons spinning in opposite directions, and thereby they cancel out their magnetic fields. Some materials, however, are permanently magnetic. They have a property called ferromagnetism. Ferromagnetic materials show magnetic properties even in the absence of a current or external magnetic field, or remain magnetized even after the magnetic field is removed. Iron being among the most common, the ferro prefix comes from this element. But nickel, cobalt, their alloys, as well as the naturally occurring lodestone, are quintessential examples of ferromagnetic materials. So what makes a material permanently magnetic? It's not just the elements that make up these materials themselves. Stainless steel, for instance, is composed almost entirely from ferromagnetic materials. But if you've ever tried to pin a magnet on your stainless steel refrigerator door, you'll have noted that it's not that magnetic. A critical feature of ferromagnetic compounds is their subatomic properties. To really understand ferromagnetism and magnetism itself, we need to delve into the strange realm of quantum mechanics, something we'll discuss further in a later lecture, because without the bizarre behavior of the subatomic particles involved, magnetism would not exist. Ferromagnetism results from two characteristics of quantum mechanics: electron spin and what's known as the Pauli exclusion principle. As a result of the field generated by its spin, every single electron has what we call a magnetic dipole moment. Basically, it behaves like a tiny magnet. Each electron can only be in one of two states. Either the magnetic field that it generates points up or it points down. When all or many of the electrons in a ferromagnetic substance are pointing in the same direction, their magnetic fields are additive and they create a larger magnetic field. That only happens, however, in elements whose atoms have a single electron or an uneven number of electrons in an electron shell. Electron shells are essentially the electron's orbits, or their range of motion around an atom's nucleus. If the element's atoms have shells that are filled with pairs of electrons, each electron will be paired with one whose spin goes in the opposite direction from its own, and their dipoles will cancel each other out. As a result, the element won't generate a magnetic field. If the element's atoms have single or odd numbers of electrons in their shells, though, the unpaired electrons have nothing to counteract their magnetic properties, and they can be coaxed into alignment with an external magnetic field. Or, in the case of certain ferromagnetic materials, they'll align themselves spontaneously. Either way, you get a permanent magnet. So that's how spin relates to ferromagnetism. But what about the Pauli exclusion principle? It's a principle in quantum mechanics that tells us that two electrons hate each other. Two electrons cannot share the same quantum state simultaneously. That is, they cannot have the same position in space and the same spin at the same time. They repel each other. Okay, but then how does a ferromagnet hang together? Doesn't the Pauli exclusion principle contradict what we just learned about how unpaired electrons can align themselves to produce a ferromagnet? Not exactly. Again, two electrons with the same spin cannot have the same position. So inside a ferromagnet, when there's an overlap in the orbital roots of unpaired electrons in the outer shells of adjacent atoms, the electrons are actually further apart when their spins are parallel or in the same direction than when they have opposite spins. And when they are further apart, the material is more stable because it has a reduced amount of what we call electrostatic energy. Essentially, there is less repellent action between the electrons, or a weaker desire to move away from each other when they are further apart. So the ferromagnet holds together after all. Now, you might have noticed that not all iron materials are magnetized. This is because the exchange interaction, which is the term for the alignment of spins related to the Pauli exclusion principle, acts only over very short distances. So the spins of electrons in small areas of the material might be aligned, but there can be many different subregions throughout the material, and the net effect can be to cancel one another out. But if you put the same substance into an external magnetic field, the small local fields will reorient themselves to the external field, and they will become internally consistent, and therefore magnetic. Even when the external field is removed then, the substance will retain its magnetic properties because the local fields have no reason to reorient once again and throw themselves out of alignment. One thing that should be clear by now is that separating magnetism from electric charges or electrons specifically is near impossible. Magnets wouldn't be magnetic without the action of electrons, and electrons can't move without creating a magnetic field. Now that we understand how magnetic fields are created by the spin of electrons, let's move on to the force that a magnetic field exerts on an electric charge. This force is what can cause the charge and the object that carries it to accelerate. Knowing the conditions under which magnetic fields can induce forces is one of the keys to understanding the role of magnetism in electronics. To be influenced by a magnetic field, the electric charge must be in motion. The magnetic field can't get the charge to move if it's not already doing so, and a moving electric charge is what an electric current is. So in an electronic device, we want to move the electric charge to specific components so that we can power the device or make it function as it's supposed to. In a magnetic field, the charge moves in a direction that is perpendicular to the direction of the magnetic field. But how do you know the direction of the magnetic field? A magnetic field includes a force, as we've talked about, and we need to know the direction of the force to predict how that force will affect the objects that come into contact with the field, and therefore how the electronic equipment might work. The direction of the magnetic field is indicated by a compass needle placed at the point at which you want to find the direction. The field travels from north to south, and the needle of a compass is, of course, a permanent magnet whose north pole is at the pointy end and whose south pole is at the opposite end. When you place a compass near a magnet, in its magnetic field, the north end is repelled by the north pole of the magnet and therefore points south, which is the direction of the magnetic field. Of course, right at the northern tip of the magnet, the compass needle will point outwards, since the field loops out before turning back to the south. You can see the pattern of the magnetic field of a magnet by placing a magnet amongst iron filings. They will take the shape of the magnetic field. Note too, though, that a given object can have one magnetic field internally and be surrounded by a different magnetic field externally. Once you know which pole is which, you can use what's known as the right-hand rule to figure out the direction of the magnetic force. To do this, place your hand, palm up, with the fingers parallel to and pointing in the direction of the magnetic field, so towards the south pole, roughly speaking. Remember that the electric charge must be moving perpendicular to the direction of the magnetic field. So if you extend your thumb, it will point in the direction of the electric charge. Then the force applied to a charged particle will be in the direction that would shoot out of the center of your palm. The rule is used to find the direction of the magnetic force on a positive charge. If the charge is negative, the force goes in the opposite direction, so towards your palm rather than away from it. Now, we can consider an electric current as simply a stream of charged particles and still use the right-hand rule to figure out which direction the magnetic field would act. But a current also produces its own magnetic field. This field follows a circular pattern around the wire in which the current is traveling, and you can use a version of the right-hand rule to find the direction of that field. Knowing the direction of the field, and therefore the magnetic force, tells you how the force is being used to move things like the mechanical bits in various electronics, like the voice coil and the cone that it's attached to in a loudspeaker. To find the direction of the field, curl the fingers of your right hand to form a semicircle and point your thumb in the direction of the current. Now the tips of your fingers point in the direction of the magnetic field. You've probably noticed, though, that many electronic uses of magnets, like loudspeakers or CD players, have circular or even coiled wires. These coils are shaped like a helix and are tightly packed. We call these coiled wires solenoids, from the Greek words for pipe and shape. Solenoids are useful in electronics because they can create a magnetic field that is controlled by the electrical current passing through the coiled wire. The force that this magnetic field creates then can vary widely, depending on how much current is allowed to pass through at any given moment in time. This variability is what makes it useful in technological applications like loudspeakers, where the magnetic force is what moves the part of the loudspeaker that generates the sound waves reaching our ears. By being able to vary the frequency of the sound wave, the loudspeaker can generate a large variety of different sounds, and we can hear the complex music or nuanced speech that the loudspeaker is designed to amplify. We can still use the second version of the right-hand rule to find the direction of the magnetic field in a solenoid, but the direction of the field can be quickly switched by reversing the current, and the strength of the field can be altered by changing either the current or the number of turns per unit length, that is, tightening or loosening the coil. These properties have been put to good use in the many applications of solenoids in our modern world, including saving data on your disk drive, starting your car, printing on a dot matrix printer, and even when you play pinball. In fact, magnets are embedded in technology all around us. The magnetic stripe at the back of your credit card, library, or other identification card is a method of storing information. Tiny iron-based particles are modified magnetically to create a unique signature readable by a magnetic reading head. Using magnetization to record information was first invented during the Second World War to record sound. Then, in the 1950s, digital information was recorded on plastic tape coated with iron oxide. Eventually, this idea was patented and applied to the use of credit cards and other forms of ID. But since the information is contained in the magnetized region, it's very easy to demagnetize and make your credit cards useless. Interestingly, it's not the strength of the magnetic field that the card is subjected to that counts, but rather the amount of time that it's been exposed to in the field. In fact, the speakers in your cell phone have magnets in them, and that's why if you put your credit cards in your pocket with direct access to the speakers of your phone, eventually they will become unreadable. Hard disk drives also use magnetism to store data. The surface of the disk is coated with trillions of tiny magnets, and then computer components can distinguish whether a current is present or not, assigning a 0 or a 1 to each magnet. Older television and computer screens produced images using magnetic forces acting on moving electrons. A glass tube, called a cathode ray tube, enclosed a gun that shot electrons via a narrow high beam towards a screen. The screen was coated with phosphor, and when the electrons hit it, a spot of visible light was generated. We still call these spots pixels, from the words picture elements, and the resolution on your screen depends on the number of pixels per square inch. An old color TV or computer screen had 3 electron guns and 3-dot clusters of phosphors that could glow red, green, or blue when struck. These dots were so close to each other that you couldn't tell them apart from a normal viewing distance. Red, green, and blue are primary colors, so every other color could be created by varying the intensities of the beams that hit each one of them. To create a picture, the beams were sent across the screen controlled by electronics, which made some parts of the scan line brighter or darker than others. At the end of the cathode ray tube, 2 electromagnets deflected the beam, one horizontally and one vertically. The current in the magnets produced a magnetic field that caused the electrons to change their trajectories to reach the different parts of the screen. This way, the entire screen was eventually covered by the beams. The number of scan lines dictated the resolution or sharpness of the image. There are now high-definition TV sets on the market that use cathode ray tube technology and have more than 1,000 scan lines. compared to the 525 scan lines of regular TVs. But for the most part, they've been superseded by flat-screen monitors. As our use of technology increases, so too will our relationship with magnets become more intense. But the good thing is that there is no evidence that magnets interfere with our health and well-being, even at large field strengths. In fact, some companies have tried to profit from the mysterious nature of magnets, claiming to have created products that can improve balance by aligning your magnetic fields or other similar interventions. Don't be fooled. There's no evidence suggesting that any of these treatments actually work. But they certainly are safe, unless, of course, you eschew medical treatments that do work in favor of one that does not. One application that really has changed the field of medicine is the MRI, or magnetic resonance imaging technology, that allows physicians to see tissues previously only visible via invasive surgical interventions. If you've ever gotten an MRI, you'll have been asked to remove all metallic items before entering the room containing the machine. This is, of course, because the MRI machine is essentially a very strong magnet. You also might have noticed that the entrance to the scanner is circular. When you're being scanned, you are in fact lying in the center of a massive solenoid. The solenoid is typically made of a superconducting wire coiled such that it is capable of producing a strong magnetic field. This field is so strong that if you accidentally brought a pair of scissors into the room, they could kill someone as they fly through the air towards the magnet. A superconductor is a type of material that, when cooled sufficiently, transmits an electrical current with no resistance. Superconductors also show the Meissner effect, which is the expulsion of the internal magnetic field. That is, when cooled to a specific critical temperature, the superconductor's internal magnetic field is zero, allowing the external magnetic field surrounding it to increase in strength. These properties of superconductors allow an electric current flowing through them to persist indefinitely without the need for a power source. And that's valuable for MRI scanners, which need to have a uniform and strong magnetic field to function properly. Magnetic field strength is measured using a unit called a Tesla, after the Serbian-born American engineer Nikola Tesla, who made significant contributions to the science of electromagnetism. MRI scanners vary in their strength, with some having a relatively weak 0.2 Tesla field, and the strongest ones in about the 7 Tesla range. Most of the scanners used for research purposes, and brain scans in particular, are either 1.5 or 3 Tesla. To put this field strength in perspective, your regular fridge magnet has a strength of about 5 millitesla, or 0.005 Tesla. The strength necessary to levitate a frog is about 16 Tesla. What? You might be asking yourself, did Indre just say she could levitate a frog? Yes, because frogs, like everything else around us, are made up of atoms that contain electrons that can shift their spins when they are placed inside magnetic fields. Now, all materials have some diamagnetic properties. They can create a magnetic field opposite to an externally applied field, causing the two fields to repel each other. And frogs are especially good for levitation because they contain lots of water and are about the right size to fit into a special type of tube-shaped electromagnet called a bitter. In the electromagnet, you can send a current that creates a strong enough magnetic field that magnetizes the whole frog in a direction opposite to the applied field. Its field repels the applied field, so the frog floats. Mice and grasshoppers work nicely too, in case you were wondering. As a cognitive neuroscientist, I both conducted and been a subject in countless MRI scans, all of which were done on a 3 Tesla machine. I've never experienced any tingling or other peripheral nerve stimulation, though some of my participants have reported such experiences. And I certainly haven't levitated, of course. But in a 7 Tesla scanner, most people do experience some slight tingling or nausea. MRI machines take advantage of the fact that our tissues are made mostly of water, with 2 protons, or hydrogen atoms for each oxygen atom. Inside the powerful magnet, most of the dipoles of the protons line up with the direction of the field, following the right-hand rule, of course. Then, a brief radio frequency signal is passed through the machine. You usually hear a bunch of clicks and then a noise of different frequency that is variable in length depending on what tissue is being scanned. This frequency is set so that it flips the spin of the protons. Then the protons are allowed to relax as the electromagnetic field is briefly turned off and the receiver coils read the radio frequency signal that is generated. Protons in different tissues relax at different rates, resulting in different signals sent to the coils. So, for example, radiologists can then tell the difference between brain tissue and bone tissue, or tumor tissue and healthy tissue. Additional magnetic fields can be generated during the scans to create 3D images, or scans can be taken over time and then compared to watch how blood flows through the brain, for example, and other tissues. MRI scans are very safe, especially when compared to the harmful radiation that results from X-rays or PET scans. The biggest worry is that some metal piece might be introduced into the room with the magnet and cause it to shift, like a pacemaker or a screw in a joint that might shift, causing irreparable damage to the part of the body in which it is embedded. But exposure to the magnet and the radio frequencies themselves has not been shown to cause any harm. Some people do experience claustrophobia because the higher strength scanners have an opening that's quite small, but lower strength ones can be quite open. In spite of all we know about magnetism and what we have been able to do with it, it remains a mysterious force that even the most accomplished physicists don't fully understand. Believe it or not, we don't really know why magnets have a north and a south pole. No one has yet explained why we can't isolate a north or a south pole by itself either, the way that we can separate negative and positive charges. We also don't really know why particles create magnetic fields in the first place. At the macroscopic level, electric currents can create magnetic fields, but what about at the micro, or more accurately, the nanoscopic level? Understanding these mysteries will occupy scientists for a while yet. We can't fully understand magnets without delving into electricity, as you've already seen in this lecture, because the behavior of electrons and magnets is tightly linked. So in order to gain a deeper understanding of how electromagnetism works and how it affects our lives, we need to turn our attention to electricity, the topic of our next lecture.